Hey guys, I'm going to go over some homework questions that come from section 7.1. Specifically, I'm going to talk about number 3, 9, 15, and 23. I think by going over these four, you'll be able to figure out any other questions from other problems, but also please check the back of your book for the solutions to help you out as well. Let's start with number 3. They're asking us to state whether we have a parameter or statistic and then use appropriate notation to describe each number. So just a reminder, a parameter is a number that comes from the population, or a number that describes the population. This could be any number. It could be mean, median, range, IQR, but most often we use the mean and the proportion. And then the statistic is a number that describes a sample. All right, so when I read this particular question, it says a large container is full of ball bearings with a mean diameter of 2.5003 centimeters. That is within the specifications for acceptance of a container by the purchaser. By chance, an inspector chooses 100 bearings from the container that have a mean diameter of this. Because this is outside the specified limits, the container is mistakenly rejected. All right, so this one was a little bit tricky, just the reading of it. So they're saying here at the very first sentence, a large container is full of ball bearings with a mean diameter of this. So they're like straight up giving you the population mean here, where the population is all the ball bearings in this container, and it's mean, so I'm going to use a mu, and because it's parameter, that's going to be the true mean, so I use a mu. So the mean is going to be 2.5003 centimeters. And then later I read that they choose 100 bearings, so right away in my mind, I'm like, oh, there's a sample. And it has a mean diameter of this. And so since that's a sample, I'm going to use X bar because that's the notation we use for sample mean. And we should maybe just make a note that mu describes a parameter and X bar describes a statistic. Number 9, a school newspaper article claims that 60% of the students at a large high school did all their assigned homework last week. Some skeptical AP students, statistics students, want to investigate whether this claim is true. So they choose a simple random sample of 100 students from the school to interview. What values of the sample proportion p hat would be consistent with the claim that the population proportion of students who completed all their homework is 0.6? So, right away, I can tell, I'm maybe just going to jot down before I read anything else. The claim is this, that 60% of the students did all their homework. That is the population proportion. So I use a P, that is the parameter. Notice they say I'm going to do a simple random sample of 100 and to interview. So I'm going to keep reading. To find out, we used Fathom software to simulate choosing 250 simple random samples of size n equals 100 students from a population in which p equals 0.6. So basically they did a simulation. They set it up from the beginning where p was equal to 0.6, and they chose 100 students, and or like 100, the sample size was 100, and out of that 100 they determined like how many did their homework or not. And again, this was just a simulation, so there's lots of different ways they could do that. They could have done it with a random number generator, could have set up the hat method, they could have a computer program that does it. Hopefully they have, it looks like they used Fathom, so like Fathom will help you make a simulation. And they chose 250 simple random samples. So here's the dot plot. So first of all, there's one dot on the graph at 0.73. Explain what this means. So I think this is really helpful to think about what each dot actually means. So that means for one sample of 100, the proportion of people doing all their homework was 73%. So again, so basically each one of those dots is representing a p hat. Okay, so every single one of those dots is representing a p-hat. If I describe this distribution, remember describing distribution goes way back to like chapter 1, where we're basically dealing with seesawks. So I'm going to go ahead and do that, and I'll just type it out. So for context, I would need to say what this distribution is. So the distribution of the proportion of students who said yes about completing all their homework is, I would say this is relatively symmetric. It doesn't really look skewed to me. It appears to be centered maybe around 0.6, and I can kind of say where they vary from. They appear to vary from like 0.47 to 0.74. I don't think there's any outliers. These are still kind of within the shape to me. So let me put all that in a sentence. The distribution of proportions of students who said yes about completing all their homework is relatively symmetric and centered around 0.60. All right, so notice I covered context, shape, and center here. I need to also talk about the spread and the outliers. The proportions vary from 0.47 to 0.74. I was careful here. Notice I didn't say they range from, because remember, range is like one specific number. So I would need to actually subtract those and find the single number if I wanted to use the word range. I kind of prefer to say where it varies. And there appear to be no outliers. All right, so that was part B. Part C, would it be surprising to get a random sample of 0.45 or lower when P is equal to 0.6? Okay, so this is a simulation when P did equal 0.6. They simulated it, and you can see that sometimes you got samples that had a proportion that was higher than 0.6. Sometimes you had a sample that had a proportion that was lower than 0.6. You know, that's all sampling variability. But this specifically says 0.45 or lower. Do you notice how there's no dots at 0.5 or lower? So that would be surprising to get a sample proportion that was lower than 0.45. And the answer, the justification would just be none of our samples did that in our simulation. All right, so it would be surprising because none of our samples had a proportion of 0.45 or lower. Let's take a look at part D. Suppose that 45 of the 100 students in the actual sample say that they did all their homework last week. Okay, so they were like, the newspaper claimed it was 60%. So the statisticians decided to see if this was reasonable. So they took a sample, and yes, it was only one sample, but think about it, guys. They only took one sample, and it only had 45 out of 100. That's extremely unlikely to happen by random chance. Notice that it didn't happen over here. If it's not likely to happen by random chance, it probably means the claim is wrong. So this 60% is not likely to be the truth, because they got 45% when they took a sample, and that is very unlikely to happen by chance. So I would say that the newspaper is likely wrong, or at least we should be skeptical. Because it is extremely unlikely to get a sample with a proportion of 45% purely by chance. Number 15, a study of the health of teenagers plans to measure the blood cholesterol levels of a simple random sample of 13 to 16-year-olds. The researchers will report the mean X bar from their sample as an estimate of the mean cholesterol level, mu, in this population. Explain to someone who knows little about statistics what it means to say that X bar is an unbiased estimator of mu. Okay, so I'm going to kind of talk about it first. If X bar is unbiased, that means that it should predict mu well when you have many simple random samples. So that's just to say with, sorry. So X bar is unbiased because you're able to use it to predict mu well when you have many simple random samples. So I could say something like this, maybe after taking many simple random samples from the group of teenagers, the mean of all of my sample means should be approximately equal to the true mean. Or another way your book said it is that the mean of all the samples should not consistently under or overestimate the true mean. So if it's unbiased, then the samples, I don't even have to say the mean of all the samples. I should just say the samples should not. So like each sample mean shouldn't consistently under or overestimate the true mean. It should be close. So picture-wise, let's suppose that the true mean is here, and these dots represent my samples. So it should, and I know this is very sloppy, but hopefully you get the idea. It should center around the true mean. Like you might have a sample every once in a while that's off, but not consistently off. It should always like sample around the true mean in order for it to be unbiased. Lastly, number 23 was a multiple choice question. In a residential neighborhood, the median value of a house is $200,000. For which of the following sample sizes is the sample median most likely to be above 250? Okay, so above 250 is like considerably farther away from the true median. So one thing to keep in mind is that the bigger your sample size is, the more accurate the statistic is going to be for estimating the parameter. So I'm going to jot that down real quick. The bigger the sample size, really what it is the bigger the sample size, the less variability, meaning it's not going to be spread out as much. The distribution won't. And with the less variability, the more accurate the statistic for estimating the parameter. So if I had a sample size of 1,000 and did a whole bunch of simple random samples of 1,000, that should be pretty close to the true median. So I know there's not a lot of information in this problem, but the key is the bigger the sample size, the better. So since this is so far off from 200,000, I'm going to choose A just because that's the smallest sample size. So if I'm only doing a sample size of size 10, it's possible that one of the ones in my sample could really throw off. Well, this isn't median. I guess it's sorry, this isn't mean, it's median. So still, I could accidentally randomly choose 10 that were like way above the true median. But if I randomly chose 1,000, then the median should be pretty accurate.